So continuing on with Chapter 4 and dynamics and Newton's laws. Just to recap, we have the first law is inertia, which is a resistance to change. It will only change if you can have inertia if you're moving, you can have inertia if you're not moving. Only change by action of an outside force. Second law, the summation of forces equal ma. That summation of forces can be many things. It could be force applied minus the force of friction, force applied minus the force of tension, tension minus the force of friction. So when you sum those together, you end up getting a net force. And if there is a net force, then you will have acceleration. Force and acceleration are vector quantities. And then the action-reaction. That means if you push on something, it has to push back equally and opposite. It's just that you might see more movement by one simply because there's a difference in masses. So what you're seeing is a reflection of the mass times the acceleration on one compared to the mass acceleration on the other. So that's a recap of the Newton's laws that we've pretty much covered so far. Right at the bottom here I've got some common forces that we're going to be using. Friction, F sub F, tension, F sub T, or T if you wish, force of a spring, F sub S, drag force, F sub D if you want, and then force normal, F sub N, or, yeah, just let's use F sub N, and then weight, W. And also it's very common to use mg for weight. So we're going to examine some cases where we use these forces. And so let's first introduce this concept of friction. So friction is a force that is dependent upon the nature of the two surfaces that are rubbing against each other. That's the type of friction we're going to deal with. So in other words, steel on steel, rubber on cement, ice on steel, steel on ice, I guess if you want to put it the other way. Just it goes on, and you can look up a table and Google a coefficient of friction table, and you'll find tons of images, and they'll give you different values for all the coefficients between the surfaces. So the force of friction is equal to mu, which is the coefficient of friction, times force normal. And so a case in point here would be that if you had a force normal, a book, such as a book sitting on a table being pulled with a force applied, and then a force of friction back in the opposite way, and then mg, which is the weight, equal and opposite to Fn. So this force of friction that I just circled is dependent upon that force normal and the coefficient that is the nature of the surfaces. So that coefficient changes depending upon the nature. You have two types of coefficients of friction. You have mu kinetic that you need to be concerned with, and that's the coefficient of friction when it's being pulled or sliding over a surface when there's movement. And then you have mu static, and that's the coefficient of friction dependent upon what it takes to get the object moving. And in our case, mu static, the coefficient of mu static will always be greater than mu kinetic. So that's an inequality sign there. It sort of matches up with the K. See if I can't get rid of that a little bit right there and freshen that up. There we go. So mu static is greater than mu kinetic. So what that means is that if you know the value of mu and you put it in, so as you can see, it takes more force to get, so this force applied would have to exert a greater force to overcome pushing that book than it would to keep the book moving. That's what it means, and it's pretty simple to follow. So if you take a look at this mu and look at the equation in general, it really follows the proportional statement, a good nice statement, y equals mx, where m is the slope. So if you were to plot force of friction versus force normal, which we will in class as we collect data on a force of friction lab, then we can see that the slope of the line should be the value of mu for that given surface interaction. So there's force of friction. Another one, force of spring, I wanted to bring up, and that follows Hooke's law. Springs follow, in general, Hooke's law, and so the force of a spring is equal to the negative kx, where again here we have k. This k is a constant, and this constant is the spring, the value, the k value, and the k value, I'll just write it here, k value is given to you in units of newtons per meter. So just looking at it, you can see if I have a spring and I want to compress it, or if I want to stretch it, either way, if it has a k value of, let's say, 25 newtons per meter, then what that means is is I have to exert a force of 25 newtons to stretch it 1 meter. And if I exert a force of 50, I'll stretch it 2, and so forth. X stands for the spring stretch. That's the spring stretch, and then this is the force. Why the negative? The negative in this general case means that if I pull on it, then the spring force will be in the opposition to my pull, to my applied force. Or if I try to compress it, it will be in the opposition to that. So this will give you the value of the spring. Again, you could do a very simple lab here, and you could stretch a spring and figure out the force acting on it, and sure enough, the slope of the line would give you that K value back as well. So two interesting little equations that give you the force from different points of view. All right. The other one is that restatement of Newton's second law, which I may or may not have already given to you, but that's W equals mg. And this is a vector, and this is a vector. And let's go ahead and go back and take a look at that. This x is considered to be displacement, and so the x in this Hooke's law. So therefore, you have a vector and a vector, and vector here and vector. So so anyway, let's get on with this show here. Weight. This is so weird how if I give you a 25 kilogram block, and then I ask you to use it in equations or to find its weight, how many students will write down 25 kilograms? I guess it's simply because you've been taught to think that that's, if you look at your bathroom scale, it measures you in kilograms. But I want you to start thinking that as soon as I have that 25 kilograms, I'm going to put it right into here, and then I'm going to multiply it by the value of g, and I'll end up with its weight in newtons. So weight is measured in newtons. And conversely, just think about it. If I give you the weight, you always have the mass, because you know that g is a constant as well. So get used to thinking about that. You can't put mass in where they're talking about weight. Weight is a force, and so its measurement is in newton. And it's always, if you're on Earth or wherever your planetary body, it'd be towards the center of the Earth, the vector, no matter whether you're on an incline or not. So going forward, let's just sort of try to tackle a statics problem, a basic equilibrium problem, to get us started with dealing with Newton's laws and dynamics. So not too much dynamics here, because it's all going to be at rest. So a classic problem would be to just suspend an object, and we'll spend the rest of the time on this this topic right here. So we're just going to suspend a sine, for instance, from Tom's Diner, I guess. Okay, and we're going to suspend it from two ropes, and we have an angle and an angle, and let's go ahead and give those angles theta. We'll call that theta 1, and this one over here theta 2. So we've got this suspended, and then we're going to try to figure out the tension in each of these ropes. And this is a classic one, and I'm just going to set this up for you, and we can talk about it and work it in class, because that's the whole point of this, is not to have me doing this in front of you. So I'm going to outline some basic stuff here. Let's use purple for this one. So if you look at this tension right here, well, first of all, let's look at the free body diagram. So you'd have T, F, T, and we'll call that 2, reading from left to right. And then we'd have, I'm sorry, I'm going to run over into it, but the FT1, and then what would be pulling down this way would be, of course, MG. And these are not to scale. So, but this is a good free body diagram for this situation. And now we can sort of go ahead and set up some simple looking at this. So let's just say that you know theta 1 and theta 2, and you know M. So if you know that, I'm going to see if yellow shows up nicely here. Then if this is an equilibrium, then this force should be in opposition to this force. So the sum of the x's, the summation of f of x, should equal 0 if I add them together. And I can get that force because if I know, going back to red now, if I know this theta 2 up here, then I also know this angle here. That's the same as theta 2, and the same can be said about theta 1. And so if you happen to know the tension, or even if you don't, you could just set it up as, continuing on here, you could say that ft1 cosine theta minus ft2 cosine theta equal 0. And the reason I say that is because remember I've said that this was an equation, a concept of equilibrium. I'm running into a screen adapter. I'll go from the bottom up. That should be an I. Q-U-L-I-B-R-I-U-M. So when in equilibrium, then we know that the sum of all forces equal 0. So there I just summed all the forces along the x, and then what can you say about the y? We could say the same thing, that the sum of forces along the y would equal 0, and I'm just going to point those out to you in a nice brown. Brown should show up pretty good. And so here's the y component of this force and the y component of this force, and so those two forces could be defined as Ft, summation of forces along the y, could be Ft1 sine theta, 1, oh, we better get our 1s and 2s in there, plus, notice I said plus because they're both pulling in the same direction, Ft2 sine theta 2. What's pulling in opposition to it along the y-axis? Well, that's mg. Minus mg equals 0. And then you'd be able to solve this problem. You could isolate out, you could solve the first equation, this equation, for Ft1, and you could substitute in and solve for the tension in this system in an equilibrium problem. Very simple, but again, if you want me to, in class tomorrow, pull me aside and we'll go over how to get it exactly. So there's a simple equilibrium problem. Let's get to some, well, maybe I'm going to try to keep it to 12 minutes, so I think I'll just talk about just some basic, let's see. No, I think I'll stop right there tonight, okay guys? And I'll put this online and hopefully you'll get to it before tomorrow's class.